so much.
Okay, I'll step out. I'm gonna hang around if you need me.
So they can see, oh, there's a chat.
It's actually set.
Exactly. Okay. Yes.
Okay.
All right, I guess we can get started.
Dr. Andrew James, everyone.
Hi, I'm Dr. Andy James, full professor in the University of Arkansas Medical Sciences Department of Psychiatry, and I'm here today to give the HED talk on statistics. What you need to know what you need to know. I have 200 years of history to cover in 20 minutes, and while I'm a fast talker, I don't talk that fast. So my goal here is to provide you some of the essentials, some of the building blocks that you can use going forward to, as you come across statistical questions, to find the information you need to help answer those questions. First off, as a disclaimer, all models are wrong, but some are useful. This is a quote by a statistician, George Box, to remind us that every model is inherently flawed. If we had all the variables we need, we wouldn't need a model to begin with. It'd be engineering, not science. So whenever you come across a model, be aware that this is our best approximation of what's going on, or it may be a poor approximation of what's going on. Some models are useful, but all models are wrong. And finally, as you embark on building a project, consult a statistician before starting your project, as every statistician ever has told me. I've been in this position before of analyzing data set that someone else collected, and just beating my head against the wall about why did you do it this way? This data cannot be analyzed. So this is again a primer. Please start off by consulting a statistician as you start your project. So some essential concepts I want to share with you as we get started. These are just key statistical terms to help familiarize you with the field. First of all, in statistics, we talk about the population. This is the pool of all individuals from which you'll be selecting subjects for your study. The population is what you're hoping to study or what you want to make inferences about. It could be, well, let me continue on to samples. Also, the sample is the subjects you selected from that population to be in your study. So if I was interested in knowing about happiness among residents, I could, my population could be all the medical residents out there or all the trainees across disciplines here at UAMS, and my sample could be those trainees in the room. I could pick you, give you a happiness scale, and hope that that happiness scale is predictive of happiness within our population. Now, a population can be a sample. This gets a little confusing, but let's say I wanted to study all of the psychiatry residents at UAMS. That would be a population. That's like a finite number. I can go give each of you a happiness scale. And if I wanted to use that scale to make predictions about all residents at UAMS, that would then be a sample. So, the concept of a population versus a sample is key, and it depends on what you're trying to make inferences about. When talking about a population, we can describe a parameter, which is some number that describes that population, like their happiness. Meanwhile, when talking about a sample, we have the statistic, which is some number that describes your sample specifically. And our goal is often to try to make some sort of inference about a population parameter from our sample statistics. Because it is very often infeasible to measure a parameter within the entire population, we acquire a smaller sample and then infer or calculate, measure a statistic from that sample, and use that as an inference for the population parameter. Now, the sample statistic that we derive from our sample, it could be descriptive, meaning it just describes our sample. If we, again, had a sample of everyone in this room, I could calculate your happiness, and that would be a measure. Or it could be inferential. We could use that statistic to make some inference about the value of a larger population parameter. So how do we go about picking our sample? There's four main ways. One is convenience sampling, where you just recruit whoever you can, just whoever's easiest for you to study. That would be the people in this room. It would be very easy for me to hand out questionnaires to all of you. Another approach is random sampling, where every member of the population has an equal chance of being in the sample. So I could get a list of all employees in the PRI and dump them in a hat and draw out 10 and give surveys to those 10 people. Every person would have equal chance of being selected to be in our study, to be in our sample. A third approach is systematic sampling, where you intentionally select every nth person in the population. So I could take all PRI employees, all trainees, whatever our population is. And if I have a list of them, I can list them alphabetically and pick every 10th person. And that is now my sample. As you can see, that's often not feasible, because who has a list of like every person in Arkansas? I mean, I guess the census has that. Finally, stratified sampling is where we recruit a sample set reflects a known parameter of the population. So going back to residents, if I know that 5% of UAMS medical residents at UAMS are psychiatry residents and 15% are orthopedic, then I would want to make sure that the sample I pick has 5% psychiatry residents and 15% orthopedic residents, so that it reflects some known parameter of the larger population. Now, needless to say, the sampling strategy influences how well or how representative our sample is of the population, but it is often limited by real-world factors like time and money and feasibility. So oftentimes we're forced to rely on less representative samples, just because we don't have billions of dollars to hand a survey to every person in the country. Okay, now there are two main types of statistical tests that you are likely to encounter. One is a parametric test here on the left. These are tests that make assumptions about the underlying parameters within your population. You might make the assumption that the mean of your population is 0. You might assume your population has this nice bell-shaped distribution. You may assume that the mean is equal to the median. These are all different assumptions that you make about the underlying parameter, and these parametric tests build upon those assumptions. You assume that you make the assumption that these are true the statistical tests incorporate these assumptions. Conversely, you could have a non-parametric test, which makes 0 assumptions about the underlying parameters of the population. And the figure on the right took me longer to create than I care to admit. So yes, you don't make any assumption about what the mean may be. Is it in the center of your distribution? Is it off on one end? What's the shape of the distribution? You make no such assumptions about the population when conducting your statistical test. So we're going to start off by talking about our parametric test, but first I want to talk about histograms. These are convenient ways of describing the frequency of observations in your samples. And I'm a visual learner. I deal in shapes, so it helps me to kind of visualize what the sample or the population may look like. A key concept, so here we have a histogram describing frequency and happiness. So I surveyed 10,000 people, this is simulated data. So 10,000 people took my happiness survey, and the mean rating here is 5, but what each of these little bins represents is the number of respondents who gave this value on my happiness scale. So you can see that it's a nice bell-shaped distribution. The range of happiness values is from 2 to 9-ish. Let's see, roughly 50 people gave a value of 3, roughly 200 people gave a value of 4, etc. So you can measure each of these individual bins, which is the number of people who gave that answer. You can also calculate the variance of the distribution. This is the spread of data around the mean of your distribution. There's a mathematical equation there for those who like math. So the variance is the standard deviation squared. which is for every data point xi, I'm already losing it all. For every data point xi in your distribution, you're going to subtract the mean, which should be x bar. I appear to be missing a bar. So subtract the mean of your distribution, square that difference, sum them all, and then divide by the sample size minus 1. So this is a way that you can quantify how closely data is clustered about your mean. And you can have, here's an example of two distributions which have the same mean, a mean of 5, but two very different variances. The sample on the top has low variance, so all the data points are tightly clustered around our mean of 5. The second distribution has high variance, still a mean of 5, but as you can see, the data points are spread out from that mean. So these approaches let us kind of visualize not just the mean, but also what's the spread of the data, what's the variance within our data sets that we're analyzing. Now, I'm sure you've encountered p-values at some point, and so I wanted to help demystify what a p-value is, because there's a lot of misconception and confusion. Typically when I ask, what's a p-value, people say 0.05 is significant, and that's, okay, well that's not true, but let's dive deeper into this concept. So let's say I gave you a quarter, you had a quarter and you tossed the coin. It's a balanced coin, you're on Earth normal gravity, I don't have any magnets under the table. What's the probability that coin toss will come up heads? 50%, right? That's a p-value of 0.50, that's it. A p-value is just a probability. One coin toss, 50% chance of coming up heads, 0.05. Now I'm showing my hand here a little bit. What if you toss that coin twice? What's the probability of it coming up heads 2 times in a row?
25.
Yes, 25%, which is a p-value of 0.25. 3 times, I think y'all can do the math here, 12.5%, 0.125. 4 times, 6.25%, p-value 0.0625. 5 times in a row, 3.125%, p-value 0.03. So a p-value of 0.05 just means that the probability of getting this result without any sort of external interference, without having a balanced coin, without a magnet under the table, is somewhere between 4 and 5 consecutive coin tosses coming up heads. That's it. There's nothing magical about 0.05. Someone somewhere long ago said that's the magic number, and it's like, 5 coin tosses. If I gave you a coin and said toss it 5 times, will it come up heads 5 times? It could. It could. There's a 3% chance of that happening. So you could, just because you get a p-value of 0.05, it doesn't mean that there's this profound difference. It could still be due to random chance. It's just highly, highly unlikely that it is due to random chance. So let's, and then a circle for illustration. So let's dive into t-tests. When talking about t-tests, it's important to take into consideration standard deviation, which is the square root of the variance if you took that equation from earlier. So let's say you have a distribution of happiness scores. Mean value is 0.05. Let's say this is, psychiatry residents, and our mean value is 5. And we want to know, is this significantly different from 0? Are we happier than 0? I hope we're happier than 0, but are we happier than 0? Well, if your sample is normally distributed, it follows this nice bell-shaped curve as depicted here, then 95% of your sample observations should fall within roughly 2 standard deviations, specifically 1.96 standard deviations of your mean. So in this example, the mean is 3, our standard deviation is 1. If we want to ask, does our sample mean differ from 2? Well, the number 2 over here is more than 1.96 standard deviations from our mean. So we would say, yes, the sample mean significantly differs from 2, p-value less than 0.05. And you can calculate exactly how many standard deviations that is. That's your t-statistic. So if you're -2 standard deviations, that's a t-score of -2. You can calculate what the exact p-value is. I'm just, glossing over things here. Let's say you have a different sample of residents, and I'm not going to say the residency, you can fill in your blank, which has a mean of 2. So, is our psychiatry residency happier than unnamed residency X? Again, I'm glossing over details. You calculate a pooled standard deviation between the two samples, but the same exact concept. Does the mean, in this example, the mean of our orange sample is more than 2 standard deviations from the mean of our blue sample? So we would conclude that the sample's means are significantly different, p-value less than 0.05. That's it. Like, it's nothing magic about it. Now, t-tests are one way of comparing 2 samples. What if you have 3 samples? Things get dicey. You could do, 3 different tests, group A, group B, group A, group C, group B, group C. But as you increase the number of tests, the chance of coming up with a false finding increases. It's kind of like the difference of flipping 1 coin 5 times or flipping 100 coins 5 times. The more coins you flip, the more likely one of those coins is going to come up heads 5 times. So instead of doing these kind of like, one-on-one comparisons, we like to do omnibus tests, which look at multiple samples at once. A very common approach, which I bet you've encountered, is analysis of variance. This is a way to compare the variances of 2 or more sample distributions simultaneously. So let's say you have 3 groups depicted by red, blue, and black. And if these 3 samples come from the same distribution, then if we ignore group membership, the variance or the spread of data across all 3 groups should be the same as the spread of data within each group, if we consider the group variance, right? I think I might be losing people. Does this kind of make sense? So like, if these 3 samples were drawn from the same population, then they should have the same variance. The variance should not differ between them. So if we ignore group membership, and we plotted this purple curve, which represents the overall variance in our sample, irrespective of group membership, these variances should be the same. They should be equal. If we divided one by the other, we should get 1. Conversely, if our samples come from different distributions, different populations, then when we ignore group membership and look at the variance across all of our data sets, again depicted by a purple curve, we have more variance than the variance of the individual samples. So we can conclude that these samples are not coming from the same distribution. They're coming from different distributions. That's ANOVA. That's it. Forget about f-tests, but that's kind of how you explain variance in these parametric tests. Now, in the remaining time, I got another 100 years to cover. So we're going to skip ahead to non-parametric approaches. And the beauty of non-parametric approaches is that they make no assumptions about our underlying parameters of our population. So we can take advantage of that. I could also talk for another 20 minutes about clustering approaches and correlation. So if y'all want to have me back, I'll be glad to do that. We do a lot of that in brain imaging, but we're going to conclude on non-parametric approaches. So one way of assessing, with non-parametric approaches, you don't know what the underlying distribution of your population is. So you build one. We call this a null distribution. You're going to look at the data in your sample, estimate what the underlying distribution probably looks like, then ask if the observed data significantly differs, p-value 0.05, than that generated null distribution. And the most common way of doing this is through permutation testing, which 20 years ago was computationally prohibitive. Now this is, in my estimation, pretty much the standard. In fact, the beauty of permutation testing is that you don't even need parametric tests anymore. And I bet statisticians would disagree with me on that. But in my opinion, we've moved beyond these assumptions about what the distribution should look like. So let's say you have 2 groups, Group A and Group B. Group A is happier than Group B. Maybe in this room, Group A here on the right are the people closer to the door. So they can get out if they have to. Like if this lecture goes south, they can head for the hills. Group B, y'all are in it for the long haul. Sorry, you're stuck here. So if we want to know, well, does your position in the room, whether you're sitting near the doors or away from the doors, influence your happiness? First, we would calculate, well, what is the observed difference between group A and group B? Well, generate a null distribution, blah, blah, blah. Typically do this like 10,000 times. And then check if our observation falls outside that null distribution. I just described this. So first we calculate what is the observed difference between group A and group B. We do this by the means. The mean of group A is 6.8. The mean of group B, 3.0. That difference, 3.8, we note it. We make a note of that. Now we're going to shuffle group membership. If your happiness is due just to random chance, then if I took all your happiness measures and just shuffled them around, or if I shuffled where you're sitting in the room, if I did this 10,000 times, I should get an estimate of just what our happiness is by like random chance. This is our null distribution. So let's shuffle our group membership. There we go. So on this first iteration, I've shuffled group membership. I calculate the new difference of group A versus group B, the difference in means. It's a difference of 1.4. I plot it on my chart. I do that a second time. The second mean, now the difference between group A and group B is minus 1.4. I plot it on my chart. Do that again. The difference of the groups A and B is minus 1. Plot it on my chart. Do this 1,000 times. Do this 1,000 times, and I get a distribution. Again, if you look at this, this is not exactly a bell-shaped curve. We don't care if it's bell-shaped or not. It doesn't need to be bell-shaped. We can calculate the bottom 2.5 percentile and the top 2.5 percentile. And if our observed value is in the top 2.5%, that's a two-tailed p-value of 0.05, then we say, yeah, the observed difference is probably not due to random chance. There's probably some systematic effect of the room that's making people over here happier than people over there. Yeah, and we do this, well, I didn't get into one-tailed or two-tailed because I think y'all might have covered that before. Then maybe that's a lecture for another time. With these new approaches like permutation testing, we can do non-parametric testing to look for differences in our samples without making any sort of assumptions about the underlying distributions. Questions? All right, thank you. And I'm sure there's a way for me to check on Zoom. Zoom. Uh-oh, are we zoomed out?
If you move the mouse to the top of the screen, then it should
Oh, stop sharing. Oh, there it is. Okay. Chat. Thank you, Lauren. It can't be that clear. Well, this will be on YouTube if you do have more questions. And do contact me or contact a statistician, someone who knows what they're talking about, who may disagree. But I think I did a good job of giving the basics.
I have a question.
Yes, please.
And it might, I don't know, might be too much for you, but what happens if during a permutation test you get a discontinuous distribution? How do you control for that?
So the question is, what do you do if during permutation testing you get a discontinuous distribution? Would that be like a bimodal distribution?
A bunch of
Like maybe you're measuring happiness and you have, several people with depression in your sample, so their happiness is lower and you're trying to figure out, well, what's going on here? It shouldn't have an effect because you're still looking for, are the observed results like within the top, are they outside that 95% range? So from the perspective of the permutation testing, there's no difference. It's
will still give you a significant result. Or can I use that to say there is a covariate in my sample, there is a bias, like half of the people in the room, half of them or some of them have
Mhm.
a diagnosis of depression, so they're unhappy by default. Or can I not extrapolate?
You can't really make, you build you build a hypothesis that you want to test, right? And then you simulate your distribution to you permute your sample to generate a null distribution, and then you ask, is the observed sample different? So, like for example, in this let's go back. I have to go back over here. So in our original example, here we have two different groups which differ quite a bit, Group A and Group B. So this could be normative control subjects and people with depression on a happiness scale. When you permute and you shuffle the labels, you're not necessarily going to get a bimodal distribution. In fact, this is simulated data. It looks, it's not that spread. But you can compare that so here this is a distribution of of the group differences. So you're saying that the observed group differences significantly differs from a permuted estimate of group differences. If group membership does not apply, then the observed difference significantly differs from what we would expect. Okay. If you have questions, email me. I can either answer them or find someone who can. Thank you. Oh, there's the chat. Oh. Hang on, there's the chat.